And happy to have Zsuzsanna Jankó talking about stability in networks.
Yes. Okay, so welcome. So first, this will be the same talk that I gave in the summit up the hill in September.
I heard that.
Yeah, so if you were already there, you can just not pay attention. So it's fine. And also this book that we are celebrating with this workshop, the market design book, has a chapter about trading networks. So now we can say that, oh, it's somehow related to that chapter. Okay, where is my clicker? Okay, so trading networks. We had 3 papers, and 3 of these people, Kleiner, Jankó, Tegita, and Boym, we are the fixed points that are all of 3 in 3 papers, and Tamura, Schlotter, and Ravi Agadesan are in one paper. So that's why I wrote it like this. And 2 of the papers are published, and 1 is not published. Should I start? So we want to talk about trading networks. So you remember the usual 2-sided matching market like men and women, hospitals, residents, or firms and workers, but I want to add some extra twist. And extra twist is that instead we are talking about trading networks. So imagine that you have something like a supply chain or something. So there are some sellers. The sellers are selling to intermediates. Intermediates are selling to some other intermediates. And in the end, they will reach the final consumer. So one version is like a supply chain can be like this, like a cyclic. Another version that we like in this paper, it might contain some cycles. So in this example, we have a coal factory that is selling something to a power plant, and so on and so on. And in the end, it comes back to the coal factory. And so in each time somebody is selling something to somebody else, it doesn't have to be the same good. So maybe the coal factory is buying coal for some place and selling energy. So it doesn't have to be the same thing that they're selling. No. So I always tell people, this is a directed graph. Just imagine a directed graph. We have the nodes, those are the firms, and we have the directed edges, those are the contracts, and each directed edge has a buyer and a seller. So yes, let's say this is buyer of contract X, this is seller of contract X. So far, so good. And like this, you have set of contracts on a graph. It can contain parallel edges if you want, and it can also contain like edges going back and forth between the same firm. So it can contain whatever we want. And let's say this guy is firm F, and firm F has 2 incoming edges and 2 outgoing edges. So it has a possibility to buy 2 goods and selling 2 goods, but we will see that this guy has some kind of a choice function. So probably they won't want to buy everything and sell everything, but pick the favorite subset. So we will call XF that those contracts that belong to firm F. And we will call it, economists will call it dancing contracts, mathematicians will call it outgoing edges, and for these, economists will call it upstream contracts, and mathematicians will call it incoming edges. And everybody will have a choice function. So every node in the graph has a choice function. Like you remember, like in students and colleges, the students have preferences over when they want to go, and the colleges have a preferences over who they want to accept. This time, the extra twist is that we have incoming and outgoing edges, and we have choice function over the incoming and outgoing edges. So what is a choice function? Just simply contracts set X has all the possible subsets, and for any possible subset, we have a chosen subset. So here are something that is offered to me, and this is my chosen subset. And we will call something IRC. Here, IRC means irrelevance of rejected contracts, which means, okay, using this beautiful picture, if I have set Y, this is my chosen set, choice C, Y, and Z is somewhere in the between. It means that out of Y, my favorite subset is CY, and Z is something that is smaller. So if this is the favorite subset out of all the subsets in Y, then it will be also the favorite subset among the subsets of Z. So it's believable. It often happens. And actually, if you write the preferences like that, that you have a strict ordering over all subsets, then obviously this will be true. But if you would like to represent it in some other way, sometimes it can fail. I want to tell you an example when it fails. Like imagine that you have colleges, and here is like two students, student 1, student 2. I just want to show you. This guy has 0 points in the admission exam. This guy also has 0 points in the admission exam. And here the quota is 1. And let's say this is contract A, contract B. Then like a choice out of A would be hiring A. The choice out of B would be hiring B. But the choice A and B together will be the empty set. This is like the Hungarian college admission system, because if you hire both, then you exceeded the quota. That's not good. And if you hire one of them, it's not equal treatment anymore. So you have to reject everybody. So this would, that would not be IRC anymore. I just wanted to give you an example that is not IRC. But now we are back to the normal IRC. So all the time in this paper or in this talk, we will use IRC, irrelevance of rejected contracts. And the other thing that we will always use is substitutability, but it's a special kind of substitutability. So let's say here you have offered contracts. Here is my favorite set, which is I'm buying one good and selling one good. And RF will mean the set of rejected contracts. So it's like this. Okay, and again, back to the two-sided market. What you already heard about substitutability. Substitutability means that if I have a bigger set, then what I'm rejecting expands. So if I can choose from, let's say again, students, there are 5 students and the quota is 3, I'm hiring the best 3 students according to the preference order. But if there are 10 students applying, and they already contain the previous 5 students, that those 2 guys who were rejected before will be still rejected, and some other people will be rejected too, so the set of rejected people is expanding. That's substitutability. But we will change this, because now we have incoming and outgoing edges, and it's not that simple anymore, because instead, just normal substitutability, you have same size substitutability and cross-site complementary. So it's like I'm selling things, those are substitutes to each other, but selling something and buying something is complements to each other. I like to, if I'm buying more things, I want to sell more things. So you can see here in this definition, but I also show you in this little example. It's first, these are the offered set, and I can buy one good and sell 2 goods, and I only want to buy one and sell one, so I'm rejecting this edge in the bottom. But now I can, one side expanded, the outgoing edge is expanded. what I rejected before, I'm still rejecting on the selling side. And it can happen that I'm rejecting something else too. So the same side substitutability happened. On the same side, that was substitutable. Yes. And cross-site complementary, originally, I'm rejecting something. So I don't want to sell this good here on this edge. But if originally I had an offered set with 2 incoming edging, so I could buy 2 things. If instead I can only buy 1 thing, that it makes sense that I'm only also selling less than before. So I'm rejecting what I rejected before, and it can happen that I'm rejecting something else as well. And all the thing together, so SS same size substitutability, cross-site complementary together, we call it fully substitutable. And we will have a bunch of different stability concepts. First, we will talk about what is a trail. Again, in a directed graph, you can have a path or a trail. So let's make a set of contracts that is coming after each other. If you have something like that, I would call it a path. But if you are also allowed to repeat some nodes, I will call it a trail. So we will use trails in our definitions. And here you are allowed to repeat nodes, but you are not allowed to repeat edges. If you would also repeat edges, then I would call it a walk. So like trail is the middle type of definition. And like you can imagine, you start somewhere and then you walk on that trail. Okay, this is a special case. We will use it later. So imagine that you have a flow, like, you know, the maximum flow problem you learned earlier, like Fulfarker's an algorithm, find a maximum flow somewhere in a graph. We are doing something similar, but now, so again, the edges are the possible contracts. S is the source, T is the target, and every node except for S and T satisfies Kirchhoff's law. That means that they have a preferences like that, that they want to buy as many goods as they are selling. So for example, this guy in the middle, maybe they are buying 0 or selling 0, or buying 1 thing and selling 1 thing, or buying 2 things and selling 2 things. But for T, because it's a target, the T just accepts everything that is offered. So it's like the choice function is that I accept everything all the time. And also, it's also special in a way that now we have strict orderings on the incoming edges and the outgoing edges. So for example, if you offer for this middle node like this, this, and this first choice, because of the Kirchhoff law, it has to pick 1 incoming and 1 outgoing. So it will pick this outgoing edge and this incoming edge. But if you order all 4 edges, then it will pick all 4 edges. So in this, before defining very precisely what is the trail stable outcome, just look at this picture. Now it satisfies Kirchhoff's law, so it's actually a flow. That's okay, it's a flow. But I don't think this is stable. Why is it not stable? Because this node here would happily switch to selling the first choice instead of the second choice. This node here is just if you can buy 1 thing and sell 1 thing instead of doing nothing, then yeah, I accept buying 1 thing and selling nothing. And we said that the targets accept everything, so the target is also happy. So instead, we switch to this outcome. And I think this is stable now, because this is not blocking, this is also not blocking, path together is also not blocking, this edge is also not blocking, it is the second, and this would be third. So I would say that this is a trail stable outcome. Okay. And yeah, and also different special case is sublight chains. So I would say that in this talk, when I say sublight chain, I mean that something is acyclic. And when I say trading network, then trading network can also contain cycles. So here, something is cyclic. And okay, first I want to define chain stability because that appeared in Ostrovsky's paper in 2008. So take an outcome. Outcome is a subset of the edges. It is individually rational if for every firm it's okay. So they accept what they have right now. And there is no trail in a way that I offer this trail and everybody who is involved, they would say that together with the existing outcome, the trail is offered. So I would accept all the edges that I included for me inside the trail. And in this case, when everything is acyclic, then it's very nice. So in an acyclic network, if we have full substitutability and IRC, there is always a chain stable outcome. And it was shown by Ostrovsky. And we can also define something like set stability, but we will also just say stable. So something is stable if not looking at trails, but any kind of set. Here you have your, okay, it's individually rational. Everybody is happy with what they have right now. And there is no blocking set. Blocking set is any kind of set of contract. You offer it, then all of the people who are involved in the set would say, yes, yes, I accept it. So we could call it set stable, or we can just call it stable. And you can see that one of them talked about trails, another talked about any kind of set. So it's a little bit a different definition. And so in Hatfield-Cominer's paper, they showed that the allocation is stable if and only if it's chain stable. And since if you have an acyclic network, you already had the proof for chain stability. So it's the same thing. So it implies that there is always the stable outcome. And somewhere else, I'm not sure if I have the correct citation or is it was proven somewhere else, but they also showed that even if it's not acyclic anymore, but in some other trading network, then stability and chain stability will be the same thing. So for set stability or just stability, you can have any kind of blocking set. The sad news is that there is not always a stable outcome. And this is a small counterexample that was also in the Hatfield-Cominer's paper, that you have just one cycle plus one extra edge. So what happens now? This guy, J, prefers outgoing edge X to outgoing edge Z. So if the starting outcome is just this cycle alone, then it's not good because X alone is a blocking contract, because J would happily switch and I would also accept contracts X instead of having nothing. So that's not good. There is a blocking edge. But if you start from the empty set, that's also not good because then this cycle is blocking because K is happy to accept the cycle and J is also happy to accept the cycle instead of the empty set, like Z and Y alone is better than nothing. So there is always some blocking set. So we are sad that there is no stable outcome. And we also showed, I will come back to it later, that in this case, determining if the outcome is stable is NP complete. So it's hard to decide what is stable. Now, a favorite definition, so that is we like the most, is trail stability. So again, you have a trading network. You can define a trail. But now we are talking about a locally blocking trail. What is a locally blocking? Imagine that this is like contract A, contract B. I don't care about this. Let's say C, D, whatever. EF. And we say that A and B together is good. Do you accept it? Let's say we have some existing outcome that we haven't, but we also have this real. So A and B together, if I offer it alongside the existing outcome, it's accepted. And later I come back and I only care about the local part. So just two edges after each other. So if I offer E and F together, is it accepted? Yes. So then it's locally blocking. And we will say that an outcome is trail stable if there is no locally blocking trail. Okay. But the trick is here that here we never asked about A, B, and E, F alone. We don't care if it's acceptable or not. But for mathematical reason, this will work fine. So we call it a short-term stability notion. So we check the two edges after each other, and then we define trail stability. The good news is that there will be an existence result. So we make a trail, just step by step, you check if it's accepted. And it also has to have a beginning. So for the first person in the trail, you just only need to check if A alone is acceptable alongside the existing contract. And that's F, G, H, let's say I. Here you also just need to check this one alone, that is it acceptable or not. And so I'm saying that if the preferences satisfy full substitutability and IRC, then there is always exist a trail stable outcome. And FJTT, that means Fleiner, Jankó, Teitel, Boym, Tamura. And I'm not going to prove this, but I'm kind of giving you the sketch of the proof. When I was going to the class of Alex, and I actually showed the proof on the whiteboard. So just for the sketch of the proof, we want to use Tarski fixed point theorem because we really like Tarski fixed point theorem. So define the lattice with the tricky partial order, where the tricky partial order means that you have two parts, and the first part is expanding and the second part is decreasing. And we will have the phi function, or phi, okay, the phi function, which means that if you are starting from a set y, z, then it's rejected, so that all of the contracts minus what was rejected. And this notation means that I'm looking at only the set z for the incoming edges, and I'm only looking at the set y on the outgoing edges. So you just combine these together, and we will say that, okay, this will be a isotone or monotone function with respect to the tricky partial order. And if you have a monotone function and a lattice, you can use Tarski fixed point theorem. Is that good?
Just a little bit more slowly. So RS ZY isn't out of Z. You are looking at the outgoing ones that you reject.
Yes, something like that.
Why the opposite?
It's a weird notation. Sorry. Actually, it looks like
RS is the product of the subset of the outgoing that you reject, and all the incoming times the y, the ones, the incoming that you reject, and all the outgoing.
And I will go to an example and I show you there. Okay. So here I had a. What was the example? Maybe it makes it a bit complicated. I get confused by your question. I think this was the picture. Contract X, Y, Z, W, and something like this. Okay, I will pick, let's say, set Z will be X and V, W, set Y will be, now I'm looking at the second line here. Everything. And I use my notation for myself that actually Z is always something with the sellers and Y is always something with the buyers. So if I'm on the seller side, I just care about this, and on the buyer side, I care about everything. This dot means that which edge, end of the thing that I'm looking at. So for this node, I'm looking at something like the incoming edges are Y and W, and the outgoing edges are just looking at X alone. Because, okay, so from here, I'm looking at the everything, so the right thing. And here I'm only looking at the Z. And from this, what would I choose? And what would I reject? I would say that the choice function, let's say choice function from this, would be buying one thing and selling one thing. And maybe in this example, X and V was the best thing. So X was the first choice and V was also this first choice.
Which node are you in your example? In the example, which node is that one?
In the example, J is this one because that has the most things listed. So that has 4 contracts and everything else has just 1 and 2 contracts. So then I would select V and X together. And I'm rejecting, okay, what I'm rejecting is like this. I rejected Y. Oh. Okay, something like this. What I'm doing here. Okay, so actually, RS means that I'm only looking at the seller side rejections, but here Z means seller side and Y means buyer side. And here is the same thing, but I'm only looking at the buyer side rejections, and here this is buyer and this is seller. So always Z is the seller. Just with the stupid notation, sometimes the order is switched. And this means that here input is Y and Z, output is everything minus what is rejected on the buyer side, everything minus what is rejected on the seller side. And that has to be a fixed point somehow. Maybe let's try if I had it correctly.
Some sense, yes, but this is the main side. Yeah,
What I have from P is Y was on the buyer side. And I was rejecting it.
I think you understood the notation.
Okay, sorry.
The product is at the end. You take the product.
Okay. Okay, so we do something like this. And in the end, we will find a fixed point because of Tarski. And we can also say that we shall show that the fixed point will correspond to a trace table outcome. So if yz would be fixed point. You take the intersection A intersection with y and c, and I say this outcome will be a trace table outcome. And another thing that we can do is just almost the same thing, just with a little bit change, that instead of the phi function, we look at the t function. But even if you do it at the t function, you will get the same solution. Again, Tarski's Higgs point theorem. And okay, this is what I showed on this whiteboard, that the sad story here is somehow these fixed points are not unique. So here you have, this is a traceable outcome, and you have a one corresponding z fixed point, and these are always the same thing, but you have three corresponding fixed points. So it's kind of not very nice. And so I wrote why it's a problem for me. It's a problem for me because in the two-sided market, everything was so beautiful, because in the two-sided market, again, you had the phi type of choice functions or the t versions. And in the two-sided market, if you could find a fixed point for a given stable outcome, it was unique. But in the trading network model, it's not unique anymore. So we had something nice earlier. You have stable matchings, men and women, and you define some choice functions and some t function, and you look at for the fixed point, and you can say that for a given stable outcome, what we will find that yz together is a fixed point of t, and it creates the given a. Then for a given a has to be only one y and only one z that will satisfy this. That's what I mean with uniqueness. I didn't prove it here, but maybe I can prove it to you later.
So somehow here the connection between the set y and stable outcomes is not unique.
Yes, here it's
the connection between
the connection is not unique anymore. Yes.
But even in the simple marriage problem, even in the simplest marriage problem, you only have generic uniqueness.
What only generate?
Generic, that is for almost every choice of the pairs.
No, she's not talking about the uniqueness of fixed points. She's talking about the connection between these two objects, between the outcome and this zy thing.
Yes.
It's not the fixed point.
So it's a connection between A and the yz pair.
Okay.
10 minutes. I will speed up. Thank you. Okay, so the speed up version for the remaining part is that terminal agents, I'm also interested in terminal agents, and something is a terminal buyer if they are only buying things, something is a seller if they are only selling things. And looking at just the terminal nodes, I want to define buyer optimal and seller optimal things. And thanks to this lattice result with Tarski fixed point theorem, we can say that there is always a buyer optimal trace table outcome, and there is always a seller optimal trace table outcome. And we also want to define some kind of partial order, and the partial order will be that something is seller superior if all the sellers are happier, but all the buyers are worse off, and buyer superior is the opposite, that all the buyers are happier. And these are opposite to each other because we defined it that way. And for this terminal superiority partial order, we want to have some kind of lattice, but it's not really working. So first we use, the law of aggregate demand. Now instead we have law of aggregate demand and supply. So it's number of contracts on the buyer side minus one number of contracts on the seller side is increasing with respect to the weird partial order. And Okay, here we have some kind of result that this phi function that we defined earlier, if we have LOD loss, so law of aggregate demand and supply, then the fixed point form a sublattice of the big lattice. So sublattice means that the union and meet operations are kept. And this is my conjecture that we were working on it a lot, but it's still not working. That for this terminal superiority partial order, we would like to have something like that it forms a lattice. So all the possible outcomes would be a lattice for this terminal superiority, but we didn't prove it. What we proved was something easier. We proved instead that you are using full substitutability and law of aggregate demand and supply. Then you are only looking at the sellers, and don't care about the buyers at all. Then for the sellers, you have a lattice property. And if you are only looking at the buyers and you don't care about the seller side, again, just for the buyers, we have a lattice property. And I would say everything quickly. So if somebody is not very happy about the original definition of trail stability, because we were only looking at the locally blocking paths, we have some kind of other definition that can fix it. So our other definition is that you are looking at the first some contracts or the last. So it's like the initial part or the ending part. So like what I had earlier, but I erased. If you had A, B, C, D as possible contracts for one given node, you are checking if A, B, C, D, let's say A, B, C, D, A, F. You're checking if A, B alone is accepted, yes. A, B, C, D together is accepted, yes. A, B, C, D, E, F. So you are only checking the initial segments. If the initial segments are always good, then we will say that it is a blocking trail, and what we define here is weakly trail stable. And because we called it weakly trail stable, that already says that somehow it's weaker than what we had before. So we can show that if something is weakly trail stable, then it's also trail stable, but not the other way around. So for example, here, together this cycle is both weakly trail stable and trail stable, but the empty set is weakly trail stable because this thing here does not satisfy this new definition with the initial segments, but it satisfies the locally blocking thing because XY is good together and ZW is good together, so it is not trail stable anymore. 5 minutes, okay. So comparing to stability, what we had in the beginning, so any kind of blocking set, is it always trail stable? No, because these exist and the other things, the normal stability doesn't always exist. So if you are looking at this counterexample, no trail stable outcome exists because it's my earlier example plus one edge, which doesn't really make sense. But this W alone is trail stable because there is no locally blocking trail, because a cycle alone would be blocking, but cycle is not allowed because the trail has to start somewhere and end somewhere to be a locally blocking trail. And okay, just for the last 5 minutes, we had this complexity result. So if you have a special case, a flow network, like everything is defined as with satisfying Kirchhoff's law, in this flow network, it is NP complete to decide if it has a path or cycle stable outcome. And for these special flow networks, path or cycle stability will be the same as stability. Therefore, it is also NP complete to decide if it has a stable outcome or not. And we can also do the same thing for general preferences. So if you have some kind of trading network where the preferences are fully substitutable and IRC, then there are two things. One is that here is the question, decide does it have a stable outcome or not. Deciding that is also NP hard. And also there is another question, the testing a given outcome. I give you an outcome and say test it. Can you find a blocking set? And just testing the instability of a given outcome, that's also NP complete. So both questions here are hard to compute. And so conclusion, we saw a lot of stability definitions. If the project, if you have a cyclic supply chain, then all of these are the same. If you have cycles, then usually they are not the same. And we want to brag about state stability a bit, because state stability, we have existence result, and it's easy to find because you can iterate a monotone function, and the monotone function will find somewhere, and that fixed point will give you a stable outcome. While if you are looking at stability, it doesn't always exist, and it's NP hard to find. Okay, and this is what I wanted to say. Thank you for your attention.
Thank you. Yeah, on questions, question for Zsuzsi? No? Köszönöm a figyelmet.
Köszönöm a figyelmet.
All right. So I'm going to be the next speaker and the last one. So I take this opportunity to thank